So thank you once again for attending our event, everyone. I'd like to welcome all participants to the third webinar under the East 101 webinar series. And if you missed our previous webinars, you can find them on our website at east101.com. We are glad to see you here, and if you like our content, we hope you will help us by spreading the word. For those of you who might be new to us, we are a specialty consulting company focused on providing advanced process engineering and flow assurance consultancy services to the oil and gas industry through process simulation technology. Our founder is a speaker today, Engineer Rafil Elyas, and we have offices all over the world, but based in Kuala Lumpur. Our track record includes projects which cover transient or dynamic simulation-based engineering services for design and troubleshooting, flow assurance analysis, operational assistance, especially the OTS, operator trainers training simulator solutions, which can help to enable safe and cost-efficient operation, as well as process simulation training. These are just some of our satisfied clients. Our work is made possible thanks to Schlumberger, which provided us with Symmetry, the process simulation platform that offers unique opportunities to integrate the models for facilities and process units with pipelines and flare or safety systems models in one unified environment, ensuring consistent thermodynamics and fluid characterization across the full system. For any inquiries, please contact Mr. Tung at the number and email address shown. More information is available on their website, www.slb.com.
I think what we can do, Zihong, is some of the details, like their contact details, Schlumberger's contact details, and our contact details. You just copy and paste some of the chat, so people can just pick it up from there.
Yep. All right. Avinash? So for our side, any inquiries about our services, please contact myself, Zihong, or my colleague, Avinash, at our respective numbers and email addresses. So, as Rafil, hi, Erwin. Sorry, I guess we covered this in our first slide, but we will take questions at the end of the webinar. And for now, please leave any questions you have in the chat box. So we will be sharing this information in the chat box as well. So please find it there for your reference. Our website is www.east101.com. As I mentioned earlier, if you missed our previous two webinars, you can find the recordings over there, as well as the recording for this one later on. Through the East 101 webinar series, we hope to cover a wide range of topics from upstream process design to downstream and refining, monitoring and surveillance, as well as analytics and AI. The webinar is scheduled to take place every other Wednesday from 4 p.m. to 5 p.m. Malaysian time. Our next speaker is already lined up. The topic that she will be presenting is compressor analysis, surge protection. Our speaker for next week is Akila Jazuli, one of our best process engineers with close to 5 years engineering experience. Kindly mark your calendars for 29th of July, 4 to 5 p.m. Malaysian time. Now, before I introduce today's speaker and topic, here are some of the housekeeping items to take note of. We will have one speaker this evening who will be speaking for about 1 hour, followed by a Q&A session. We kindly request everyone to stay muted to avoid noise and interference. If you have any questions throughout the presentation, please put them in the chat box and they will be addressed by the presenter at the end of the webinar. If at any time someone is experiencing difficulties with the stream, please check your internet connection and reconnect to the webinar room using the same link. If you miss anything, not to worry, the recording will be available within a week on East 101's webpage under the Events tab. So today's speaker is Engineer Rafil Elyas, the founding owner and principal engineer of East 101. He will be speaking on the topic molecular PIONA-based feed characterization and refinery reactor modeling. Since graduating from Syracuse University with a bachelor's degree in chemical engineering, Engineer Rafil has accumulated over 30 years of experience in the industry. He has close to 15 years of formal training experience since he started lecturing, over 15 years, since he started lecturing for the John M. Campbell Group, and currently runs training courses via East 101 University. He is currently an industrial advisor and adjunct lecturer for Nottingham University, UiTM, and UTP, as well as a chartered engineer and fellow of the Institution of Chemical Engineers. Without further ado, I will invite Engineer Rafil Elyas to share his expertise and know-how with us.
Okay, thank you, Zihong. I think I have got control of my slide now. So let me just stop sharing the screen for a bit and I'll share it back. Good afternoon, good evening, good morning. I think we've got people coming from all over the region and all over the world. Thank you very much for taking the time to join our session. This is our third session, as Zihong had mentioned. I notice we have a lot of friends coming in from Indonesia. So selamat siang, selamat datang. Very happy to see everyone here. So I'd just like to, I'm just going to share my screen now. I'm just going to, I guess, lay down some agenda. I hope this is right. Okay, there you go. So just to talk about the objective, and I want to be very clear on this. Just to be clear, what I'm going to be doing is I'm just kind of sharing my experience on this, what I consider a fairly new method of fluid characterization and a pretty interesting way of looking at reactors and flow sheets, which is using a reduced order model. So I just want to clarify one thing as well. We've not we've not done any benchmarking analysis using this tool as yet. Or using this methodology, but we've used it internally to take a look at some refinery modeling opportunities. Yeah. So just as a disclaimer, I'm not going to be showing like any benchmarked models. I think if you probably approach Mr. Tung from Schlumberger, I'm sure they've got a whole bunch of white papers that describe all of that. Yeah. Another thing this is also not going to be is we're not going to be going into like a software demo. I'm kind of just going to be talking about the overall philosophy of this this particular way of modeling and characterizing fluids. So onto the agenda. Whoops, I've gone back. Okay, so the agenda is as follows. First thing is we'll take a look at fluid property requirements in a process of chemical engineering, particularly in oil and gas. And in this particular example, particularly for downstream implementations. Yeah. We're going to be looking at some of the traditional methods that have been used for this, and we'll also later go into this, what I refer to a new method of fluid characterization using a molecular compositional model. After that, I'll show you how some of the reactors are set up and introduce this concept of a reduced order system. Reduced order system, I guess back in the 90s, if anyone was here in the 90s doing computing in the 90s, these were kind of, I guess, referred to as neural net models. And I think HISIS in the early days, in the 90s, had dabbled with implementing neural net layers to make the reactors move faster. I'm really sorry, I'm getting some noise from my phone. I'm going to turn that off. I didn't realize it was on. Okay. So let's take a look at fluid property requirements in process and chemical engineering. So here I'm showing your typical asset life cycle. So some of this I've kind of covered in the 10 commandments of process simulation, which is the first in the set. I'm just going to skim through this really quickly. If we take a look at the typical asset, and this can be any kind of asset, it could be an offshore facility, it could be a downstream facility, refinery, FPSO, etc. So these are some of the typical activities that go on. Yeah? You start off with a new opportunity, do some feasibility studies, conceptual design. You later move into basic design or FEED, detailed design, construction, commissioning, startup operations. Once you've been operating for a while, you start taking a look at improvement, extensions, revamps. And in some the cases, there's going to be at some point in time, if you're operating, say, a topside facility or an FPSO, when you're having a decline, you might be decommissioning your facility. So if you take a look at all of these steps, all of these particular areas, you're going to be doing some form of computation or simulation. Yeah. Any kind. It could either be doing a flowsheet simulator like Symmetry or HISIS, Unisim, Pro2, Aspen Plus, or it could be a fluid flow application like Olga or PipeNet, PipeSim. There's a range of applications. So I think nowadays you can't get into an engineering office without seeing some kind of modeling or simulation being done. Just before I do it, I'm just going to ask my team over here, is everything coming over okay, the video and the voice?
Yes, it's perfect.
Okay. So again, if there's any questions or issues, just push them in the chat box. Yeah. So I'm just recapping here the 10 commandments, what I refer to as the 10 commandments of process simulation, very quickly. You know, understand your objective, identify your system or your process, imagine what's going on physically, determine what sort of mathematical model is required, so you know what kind of software to buy, you know what kind of options to choose, know your components, know where your feed details are coming from, where your feed compositions, conditions are coming from, know the boiling points of your components, know the properties, particularly boiling points. That's really important. The rest are pretty much what I would consider probably a common sense for most engineers. Keep track of units of measure, perform heat material balances first, and plot your phase envelope. So you notice over here, I've got 3 items over here, 5, 6, and 7, which are essentially about the components of the feed. It's really important. So I've actually, of these 10 items, 30% of them have to do with understanding your components and your feed. Because if you don't have your feed properly characterized, everything else is not going to be correct. Yeah. Okay. So let's just take a look at your typical hydrocarbon supply chain. And I'm starting off from the reservoir. So I'm a chemical engineer, and for a chemical engineer, I think that's what a reservoir looks to me. So we've got essentially some gas, oil, and water trapped between some impermeable or cap rock. You have a drilling and processing platform. Bring up your hydrocarbons, impurities, separate them at the production. You have some production conditioning happening in an upstream facility. Then you feed your hydrocarbons to a downstream facility or a midstream facility, refinery or gas plant, where you do a first step of separation. From here, you might be distributing fuels. So like if you go to Kirte, you'll see all the hydrocarbons coming from offshore, landing at the onshore gas terminal or the onshore slug catcher, and then being piped to a refinery or gas plant. Yeah, and then the fuels sent to distribution or export, middle distillates, or some of the ethylene would be sent to petchem and petrochemical products. So this is a typical supply chain. And today I'm going to talk about roughly two of these areas, production upstream and some refining. Can I just ask everyone to please mute your microphones for now? Thank you. So I'll be talking about both of these areas, production and conditioning and processing and treatment. But primarily we will be focusing on, that's my laser pointer, on refinery today. Yeah. But I'd like to talk about some of these other areas first. Okay, so we're talking about feeds and properties, yeah, fluid characterization and various properties. Let's take a look at the typical kinds of properties that we would be interested in. So I've got, again, a sketch of an upstream facility. So I've got my hydrocarbon reserve. I've got a well choke, a pipeline, and I'm bringing this to a topside facility. And the topside facility, I've got some bulk separation. I'll be sending my gas to compression, gas injection, gas lift export. I'll probably be doing some dehydration with the gas. I might have some TEG dehydration, or in some of the cases, we have CO2 acid gas removal. We might have some membranes, or in some cases, some amine systems. For the oil, we'll generally be dewatering the oil and potentially stabilizing it in some cases. If it's an FPSO, you'll be stabilizing it and putting it in the storage tanks in the hull. Otherwise, if it's a central processing platform, you might be sending that to an onshore facility. And the water is generally going to get treated, produced water, and it'll be used as water injection or sent overboard. So you'll be removing all the hydrocarbons from there. So if we take a look at this, what kind of engineering calcs do we do? Well, I think we've got in our audience today people coming in from upstream and downstream, yeah? But I guess we've got some common computations that we have across the board. So if you take a look at an upstream facility, on the pipe, we typically are going to have some kind of a design computation that we'll be running, diameter, layout. When you do your field selection, you'll be taking a look essentially at the hydraulics in the system. And later you'll be doing some flow assurance, transient fluid flow using an application like Olga. And you'll use this for liquid management, slug control, slugging management, wax management. You'll be using this tool to figure out how often you need to pig the line to scrape out the wax or to sweep out the liquids. And you'll be doing some hydrate analysis where you're going to figure out how much methanol or MEG you need to inject to make sure that the hydrate formation temperature is significantly reduced below any temperature profile in your system. Yeah. So we take a look at this for the pipeline. If we take a look at the facilities, the facilities go pretty much across the board. You're going to be looking at separator sizing, compression systems, rotating equipment, compressors, pumps. You'll be taking a look at piping, nozzle design, stabilization, vaporization, condensation of your fluids. All of that happens on your topside facility. Okay, so what kind of properties do we need? Yeah, so this is always the first thing that you think about when you're starting your simulation. And I'm going to kind of divide the properties over here into groupings. So the first is what I'm going to refer to as thermophysical properties. Thermophysical properties are generally properties that are going to feed into the thermodynamic functions that we use for a lot of our process engineering. And these, we'll get into that in a few slides down the road. But some of the thermophysical properties they're talking about are like density, molecular weight, vapor pressure, PSAT, heat of vaporization, CP, gamma, CP over CV. These are thermophysical properties, which essentially consist of the bulk of the properties that you're using when you do your steady state simulation in your flowsheet simulator, whether it's Symmetry or HYSYS or Unisim or Petrosim or Pro2. So I'd say about 90% of the kind of properties that you're using are going to be thermophysical properties in nature for most of your heat material balance and engineering sizing calculations. Yeah. So that essentially covers a lot of the facilities. You need that as well for your pipeline, and if we've got any of our visitors or participants who are reservoir engineers, you'll essentially be looking at this as well when you do your reservoir modeling. The next important part, transport properties. Now these are always a bit tricky. So you guys who've been doing a lot of flowsheet simulation for a while know that, hey, gas transport properties, they're okay, but liquids are always a bit iffy. Because let's say if you've got oil and water, you might be having emulsions forming, and that changes your overall viscosities a lot. Yeah. So transport properties, typically we're looking at those when we're looking at pipelines, or when we're sizing any equipment that needs to move the fluids and move the liquids, like pumps. Yeah. The next, and you don't see this so much upstream. At least, okay, I should say I don't see this too much upstream because I'm doing primarily process and flow assurance. The chemistry. If you're doing flow assurance, you'll see chemistry kind of creeping in when you're doing wax predictions. If you do a lot of wax predictions, you're generally going to be requiring GC results to C60 or C80 paraffins. Yeah. You also have some chemistry requirements when you're looking at corrosion. Yeah, so there's some chemistry requirement upstream, and there's depending on what area you're in, the amount of chemistry that you use can vary. For most process engineers, flow assurance engineers, the chemistry for upstream is primarily going to be focused on wax type of issues. So this is upstream. What about downstream processing? So downstream is a bit different. Yeah. So downstream, I've got some fluids which are kind of nice and clean and well behaved, and they're stabilized and they're sitting in atmospheric tanks. If they're liquids, I might have like a gas storage coming from a sphere feeding into my system. If I take a look at my facility, and I'm just going to do a very rough sketch for this, generally I'm going to have some fractionation, probably followed by, well, I might have some treatment, reaction, and purification. Yeah, so in general, you're going to see this in most of your downstream facilities. And then you'll have some nice clean products, which you'll keep in atmospheric tanks, or if it's a gas, in some spheres. So if we take a look at these processes, we can get by for most of the work that we're doing using thermophysical properties for fractionation, compression, rotating equipment, etc. Yeah, you can get by most of the time with thermophysical properties. When you're looking at more detail in your distillation towers, if you're looking at hydraulics, then you need some transport properties. If you're looking at tray hydraulics, yeah. But most of the heat material balances, again, I think about 90% of the work that you're doing for your fractionation blocks are generally going to be requiring thermophysical properties. Density, molecular weight, PSAT, heat of vaporization, and sensible heat, CP. Now, this is where the chemical engineer comes in. This is why we spend 4 years in chemical engineering school if you're a chemical engineer. And this is why we take about 6 semesters of chemistry. At least I did 2 semesters of general, 2 semesters of organic, and 2 semesters of physical chemistry. When we're looking at reaction systems, reaction and treatment systems, This is where we need to understand molecular definitions. We need to understand reaction mechanisms. We need to take a look at stoichiometry. We need to have a handle on very specific energies, heats of formation, which we then use to estimate heats of reaction, Gibbs free energy. And all of this information, heats of formation, heats of reaction, they depend on understanding what the chemical structure is. Yeah. So if you remember from school, the way we calculate the heat of formation of a compound is we sum up all the heat of formations of all the individual constituent components. We use that as a basis. So heats, in order for us to calculate the amount of energy that's involved in our reaction systems, and again, the energies are then going to impact your kinetics or your mechanisms. It's important to understand molecular structure and glean a lot of information from there. So let's just bear that in mind for a while. So this is for downstream processing. Yeah. So that's my extent of organic chemistry. If you take a look at if you're using a standard process flow sheeting tool, Symmetry, HYSYS, Unisim, Petrosim, you'd see something like this. You'd find a component database where you have a library of common components: methane, ethane, propane, CO2, amines, everything, the whole kit and caboodle. I think there'll probably be more components that you would typically need. I can't remember how many components they have in Aspen, HYSYS, or Symmetry. Thousands, order of magnitude 2, 3, 4,000 components. So these are what we refer to as, I'll call these library components. So these are components which are stored in your simulator, and they come with all the various pure component properties. Yeah, base properties like the normal boiling point, molecular weight, standard liquid density, and other properties which are required when we perform thermophysical property calculation. Critical properties: acentric factor, dipole moment, heats of formation, Antoine coefficients, viscosities, transport properties as well. Yeah. So these are generally, when you buy a simulation tool, all of this is in the data bank. You don't need to input any of that. So there is another class of components, and they like to call them hypothetical or pseudo components. You might hear these terms being used. So if you're upstream, you're working upstream, then your hypothetical or pseudo components will generally be something like your plus components, C7 plus components. Yeah. If you're downstream, then this will essentially be your assay, either your crude oil assay or your product assay, your gasoline, straight run naphtha, etc. Yeah, and these are generally going to be in terms of like some kind of a boiling point curve representation. Yeah, so the way these pseudo components work, they're not in the system, so you need to input information. So if you've got like a C7 plus component, you would input some base properties, normal boiling point, liquid density, molecular weight, and then you press the estimate button, and magically all of these components, all of these properties occur. When you're inputting boiling point curves, same thing happens. You essentially put in, like, using the boiling point curve, you can estimate your boiling point. You might also have a density curve. You put in the density, and you have this hypo generation tool which estimates all of these properties for you. Yeah. So once you have all of these properties in place, for refining or refinery or downstream, you might also input some additional user properties or refinery properties which are important for you. Pour point, if you're looking at diesel, cetane index, and PIONA. Yeah, paraffins, isomers, olefins, naphthalene, and aromatics. So sometimes you can take that information, you can kind of attach it to your hypothetical components. We'll talk about that a little later. So after you put all this information, all your components are nicely prepared, you create like a component package, then you send it to a property package. So the typical ones that you'll see if you've been brought up on the Symmetry or HYSYS universe, if you're doing upstream oil and gas, typically you see Peng Robinson. Downstream, you'd probably see Peng Robinson as well. If you're in a petrochemical facility, if you have azeotropes, then you'll have an activity coefficient model like NRTL. So these property packages, what they do, well, they take all of these this information here, and they start generating all the properties that you need to do your engineering calculations. Your fugacities, fugacity coefficients for your vapor-liquid equilibrium, activity coefficients, all of your thermophysical properties, and your thermodynamic properties as well. Enthalpy, entropy for your rotating equipment, Gibbs free energies for your reactors or even your hydrate formation. Yeah. So that's all this information ultimately is going to feed into your process simulator. So that's typically how things move, and that's generally how you would essentially set up your model traditionally. Okay. So those are the components that's within your simulator. So now let's take a look at fluid characterization. Let's take a look at how you typically handle data and how that data fits into your components. So let's take a look at some typical lab analyses for fluid characterization. So for those of you who are upstream, you're going to rely on a lot of chromatography, either GC or high temperature liquid chromatography. And based on that, you're going to get molecular definitions or molecular compositions based on standards. What do I mean by that? Well, in your report, you'll see methane, ethane, propane, isobutanes, etc. But are you sure that's the components coming through? Well, that's our best guess. Why? Because we run some standards, standard methane, standard ethane, standard propane, and then we take a look at their retention times. So anything that gets injected with which shows that the retention time is most likely going to be that molecule. Yeah. So these molecular definitions are generally based on some form of standard or calibration. And once you start getting your details, I'm not going to get too deep in fluid characterization over here. You might have some heavier components, plus components. You might take those components and push them through some kind of a PVT tuning application, like PVT sim multi-flash. And you'll have a list of components here, your C1, C2, C3, C4, and your plus components, C7 plus heavier components. So these will all be, these heavy components, plus components will be generated by your PVT tuning application. Okay, so downstream, if we take a look at some of the lab analyses, a very, very long time ago in the early part of my career, I used to work over at Petronas Research and Scientific Services before there were two S's. Now it's just PRS. Back then when it was PRSS, they had a TBP lab, which ran TBP, D86, D1160 analyses. So we'd be essentially performing boiling point analyses on the fluids. So this is an example of maybe like an ASTM D86, which is a single stage distillation. You'd put in your fluid and then you'd boil it off, collect various volumes. Then you'd take measurements, boiling point. You note the temperature when these components came off, and then you'd essentially construct a boiling point curve. You'd also take these samples and then run them through a refractometer to calculate the refractive index, which would then give you the density. So you'd also get a density curve. Then you'd also run the transport calculations as well, yeah, to get the viscosities, surface tensions, etc. So now, after you've got this information in these boiling point curves, you would then, in the simulator, use the oil characterization tool to generate hypotheticals. And if you've been using the common tools, you'll probably notice the naming convention NBP 90, NBP 105, etc. And these NBPs are essentially representative of these lumps of components that boil at those temperatures. Yeah. So you essentially write this curve and then you cut it at various temperatures, and you get these slate of components, boiling point components. You might also perform some PIONA chromatography, which is essentially a chromatography process, to actually associate PIONA characteristics to each of these boiling points. So what you might find is typically for each of these boiling points, I'm going to attempt to go to my pen to see if it's going to work over here. Okay, I'm here. So each of these components would have their own PIONA representation. So this guy would have a PIONA representation. This guy would have a PIONA. Yeah, so each one of these would have all this information stored typically. That's traditionally how it would be done. Okay. So what happens is this kind of results in a fairly limited resolution. Yeah, so we don't really get a lot of chemical structure detail associated with these normal boiling point components, and that becomes a problem later on. Yeah. So if we take a look at that, what can I use these components for? Well, these components, as I've shown earlier, they're great for calculating thermophysical properties. We can pretty much do, we've got enough understanding, enough algorithms to calculate thermophysical properties. There's reasonable resolution on here. Transport, the gas, it's okay-ish. For liquids, tends to be a bit poor. So when you're doing, if you're a process engineer and you've been sizing stuff, you've been sizing pumps, you've been doing internal calculations, you're going to find that a lot of times you don't really use your liquid viscosities from your simulator, right? You're probably going to use the lab results. So you would use your simulator to get the HMBs, to get the flow rates, and then you get your lab data to get these bulk transport properties for all the various phases, to use that for your sizing. Yeah, that's traditionally what we would do. Sometimes if you're lucky, you might be able to input like a viscosity curve or something traditionally, and that's one way of doing it. But again, when you're taking a look at emulsions, it's quite difficult to predict because it's actually fluid mechanics. Yeah. Chemistry and reactions. From here, I kind of have a fairly low resolution on that. So a light ends, it's okay. Yeah? I can see my molecules over here. So if I'm doing like an ethylene cracker or something, I'm okay-ish. If I have like a steam reformer, I can kind of get by on that. But if I want to try and use this information for a naphtha reformer or hydrotreater, it gets very challenging. Yeah. So I'm just going to make one slide and talk about PVT for upstream, and that's pretty much all I'm going to be discussing on PVT for now. From now on, we'll be talking primarily about downstream. But I'm just going to make one statement for PVT, for upstream applications. For most upstream process or flow assurance applications, generally your PVT tuning is going to provide decent property representation. So whether you're using PVT or multi-flash, yeah, using chromatography, bulk lab analysis, and these tools, you can get enough resolution to do most of your work. So the kind of study that the kind of fluid characterization that I'm talking about now, that I'll be talking about today, using these molecular definitions, PIONA slate definitions, you can use them upstream. They do give you some benefit. But they're from my, and again, this is my opinion. Yeah, I think PVT multi-flash seems to be the go-to application for most of the practitioners in this area. So that's all I'm going to say about upstream. So downstream, we've got some issue downstream over here. So as I've mentioned, we have limited resolution with the normal way of doing things, with the true boiling point, with the boiling point curves, and associating, lumping in PIONA characteristics with each of these individuals. So it's okay for light ends, but it's challenging for heavier liquids, heavier components. So let's just take a look at your typical refinery now. So I'm not going to get in, I'm not going to be talking about refinery modeling. That's probably worthy of a different discussion. Because again, today I'm just going to be talking about a different way of fluid characterization, which allows us to represent reactions in a more efficient manner. So everything in red clouds over here is a reactor. We have a lot of reactors. Actually, there's some which I haven't, I've left out the hydrocracker and some of the other reactors. So these reactors in refineries can be extremely complex because they're not like the kind of reactors you see when if there's any students around here, when you're doing your kinetics class or your organic chemistry class, you've got some nice equations and nice kinetic expressions. You don't have that in this case. Yeah. In fact, most of the time we don't know traditionally when I was just starting my career, we didn't really have many tools to model refinery reactors. So what we did was we primarily modeled that as a black box with a mass balance and a heat balance. So the way we do it is we would create, let's say if I wanted to model a reformer, yeah, like a naphtha reformer. So I'd be taking light straight run naphtha. I might get like a D86 characterization for that, and then I create my component slate, and I'd assign that to a stream in my simulator. I take the reformate, I go to the lab guys and say, please give me the D86 for the reformate, and I would, again, create a new slate. So I've got two slates of molecules here, a green slate and a purple slate. So they're both different, yeah? One is my product, one's my feed, another one's my product. So if you're using any of these tools, I refer to them as, I guess, the Craig Morris family of tools. So that would be HiSim, HiSys, Symmetry, Unisim, and Petrosim. They work on a similar computational framework. You'd find something called a balance. So it'd be a mass balance and there'd be an energy balance. So the way we would do this, it would just input this feed and we put in the products. So there's no reactors model. It's primarily for HMB, heat material balance generation. So it's not predictive. You can't predict yields, but you can use it to do all of your, your heat exchanger, heat exchanger analysis, a bit of troubleshooting around all the other equipment except for the reactor, because you won't be getting yields, which is fine because most of the time when you're in the refinery, when I did my stint over at Curte Refinery as a young engineer, most of the time you're not really going to be modeling the reactor as it is. Most of the time, if there's anything wrong, you just call up the vendor, IFP or Exons, and then you yell at them. These days, though, we want to get more visibility on these reactions. So it's not an option to just look at this and call up the vendor whenever there's a problem. Most process engineers want to have some visibility on the reactors. So this mass balance methodology is okay. I think you can get quite a bit of the job done. But sometimes as a process engineer working in the field, you want to know how long you're going to be able to run your CAT before you start looking at the activity. You start seeing reduction in the activity. Yeah. So you want to be able to have some kind of a model for that. And you can't do that with this. So I'm not sure when all this came out. Back in, I guess, the late 80s or 90s, some software tools started coming out. And I think the earliest one that I saw was from a company called KBC, who are now owned by Yokogawa. And they came up with this sort of lumped kinetic model. Yeah. So you would essentially, it'd be as follows. You'd essentially have your straight run naphtha. You'd generate some normal boiling point components. So everything in green here would be, imagine this to be your flow sheet, yeah? So these are your flow sheet streams, and you have these component slates, one set of component slates. And they would essentially provide reactor models. And these reactor models would actually have some form of molecular definition or lumped molecular definition. So it won't actually be individual molecules, but you can say like C5 paraffins. If it's an isomerization, they might go to C3 and C2s, or if it's C7 paraffins, straight chain paraffins, it might go to like a C5 isomer. Yeah. So you've got all of these reactions, and I'm still really bad at organic chemistry. So whenever I have an organic chemistry question, I've got a couple of go-to chemists that I typically bug to help me with some kinetics or mechanisms. So actually, let me go back. So now notice this. I've got like a set of hypothetical components, which I've talked about earlier. I've used this assay generator, and I've got these placeholders, these component slates, some library components. Some of these are normal boiling point components. But in the reactor, I have all of these sort of molecular definitions. You find what happens at the boundary of these reactor, you have to have some form of a mapping. Yeah. So we generally refer to that as molecular decomposition. So if you want to get fancy, you can call it molecular decomposition. Meaning I've got this lump, this NBP70. This NBP70 has to map to a range of components. So NBP70 might be a lump of maybe C4, C5, C6. And somehow over here at the boundaries here, I need to then map them to individual molecules. After the reaction's done, I got to remap them out again to the flow sheet. Yeah. So I think if you've been using tools like Petrosim, HYSYS refining, some of the aspirin refining tools, you're generally going to find this is how we do it. If we've got anyone from Rapid over here from Pengerang, this is generally how your models work. So these two red bars here, they're red for a reason because they're a pain to set up, and they're pain to do the mapping. So sometimes there's a bit of automation. Sometimes we have to do some hand mapping to map the boiling point components to the molecular definitions. Yeah. And you can imagine you have a headache if you have a recycle. So you have this stuff coming back in again. So that can be rather challenging computationally. So this is how some of the traditional tools, I guess the more modern tools. By modern, I mean everything 1990s. To me, that's modern because I went to school in the 80s. So yeah, and that goes for my music as well. I think any records issued after 1990 for me are still new music. So is there a better way to do this? Yeah, well, obviously, that's why we're having this talk. Rather than So, sorry, I think someone had said something. I hope everyone's okay there. Avinash, Xiong, am I coming in okay? Can everyone hear me?
Yeah, sounds good.
Okay.
Perfect.
So is there a better way of doing this? Well, one of the things we could do is we could look at characterizing the molecular components from the beginning, rather than having all of that TBP analysis and mapping. Yeah. So rather than having these reactor sets and having external sets, we might as well start from the beginning with that. Yeah. So notice one thing though. When you look at these kinds of representation, you got heck of a lot more components than you do when you're doing your TBP characterization. So if any of you have done like crude characterization, you might, if you're doing like a crude tower or some of the reaction modules around there, you might have maybe a slate of about 20, 30, 40, 60 components maybe. But when you start going down to here, you have a lot more, and I'll show you how many components get generated. Then it's a whole bucket load of them. Why didn't some software companies do this in the past? I mean, it doesn't sound like rocket science, right? Well, I'm not a developer, so I can say things like that. Well, this is why. So when I started going to uni, we were doing things like this. So I'm just gonna show something up here. I'm just gonna take this point to have like a quick break. To show you something. So we're going to run like a little competition over here, and we have some East 101 t-shirts for this question that I'm going to ask. So I've got 3 sets of computers here. Something over here, 1, 2, an IBM a mainframe, an IBM PC, and the most recent loaded MSI gaming machine, gaming/simulation machine. So let me turn this off. So for the first 3 people, Avinash, can you see me on the screen?
Yes, I can.
Okay, so the first 3 people who type in, tell me what this piece of, what this thing I'm going to flash up at the screen is. The first 3 people that send it in, send us your email address, and we'll send you an East 101 t-shirt. So this, first 3 people tell me what this is and what it's used for. Can you see that, Avinash?
Yes, it's clear.
Okay, so if you know what it is, the first 3 people send, the first 3 correct ones will get an East 101 t-shirt. So make sure you tell me what it is and put your email address on there. Yeah. So this goes into one of these devices, and it definitely doesn't go into your MSI or Alienware device. Okay, I'm back on the screen. Avinash, can you see the screen?
Yep.
Okay.
Perfect. Fine.
So what I didn't do in the past, well, now we have cheap and fast computers with a lot of cheap memory, because we need to have a lot of components. And if you want to have that many components, you're going to need a lot of memory. If any of you have done simulations, particularly dynamic simulations, the more components you specify, the slower your simulation runs. Yeah. Okay, so now I'm going to talk a bit about the molecular composition model. And so you might hear this referred to as your molecular composition model, or the molecular decomposition, or PIONA slate, or PIONA molecular slate. It's all a similar concept, yeah, similar concept. And again, I just like to stress that I'm not going to get very deep into this. So this is just a bit of a sharing. I recommend that if you're doing refining work, and if you're working with reactors, then this is probably something that is worth looking at. And this is actually when the company came up with this. Right now, the software is owned by Schlumberger. Prior to that, it was owned by this small Calgary-based company called the Virtual Materials Group, VMG, who are former colleagues of mine. So when they came up with this, I thought, hey, that's really neat. That's a really interesting way to represent fluids, and I got interested in it, and I started. We started experimenting with it a bit. So again, we've not done any benchmarking. I see there are some of you guys from Refinery. Presumably, I think there's some guys coming in from some team, some ladies and gentlemen from Pertamina. You guys have a lot of data. Also, I don't know if we have anyone from Pengerang, but you guys have like a whole load of data, which would be great for benchmarking these kinds of cases. So let's take a look at this molecular compositional model and see what it's all about. Okay, so if we take a look at this, this is a screenshot from Symmetry. You might hear it referred to as VMG Sim or Icon, but this is pretty much the layout. So what I have here is an RFCC, yeah, model. I'm getting feed. In this particular case, I've got feed from vacuum gas oil and vacuum residue. I'm blending it here, and I'm putting it into the FCC unit. We'll go into talk about that a bit later. And then the products, the reactor products are essentially being sent to a column. In this particular example, we're using a simplified column. So it's not a tray-by-tray column. In this case, just to facilitate some computations, we're using, I guess there's different ways of referring to these columns, the sectional columns or K-based columns or something like that, yeah? But they're not tray-by-tray, they're like sectional, probably sectional K values. So in this case, let's take a look at these two feeds, vacuum gas oil and vacuum residue, yeah? So if we take a look at this, these analysis, what we would typically do is we would input, take a look at what kind of data we have. So in this case, we have some distillation data, which would generally be a vacuum distillation, so D1160. So it'd be like a single stage unit, single stage apparatus, and we'd be generating like the D1160 curves. Now, after we generate this, with this tool, something interesting happens. Once we've generated, we're at this point in time, we're still in the fluid package. We're still in the basis environment. at this stage, there is what I refer to again as a molecular decomposition algorithm. So what we do is we take a look at these cut points. We take a look at the boiling point curve. And we actually compare it to some target values, bulk PIONA, bulk specific gravity, bulk SARA, bulks pole points, etc. And then based on that input, it will generate a slate of components, molecular-based components. Notice these are not actual pure components. Yeah, you have some pure components up here, C1, C2, C3. At the top over here, it's in a badly drawn benzene ring. You got some of these other components. So these are still kind of lumped a bit, but there's a bit more chemistry and a bit more resolution around there. So these components have chemistry definitions on them. They've got heats of formation, they have free energies, etc. And what we have is from this TBP curve and this algorithm, we now can arrange this in what we refer to as this PIONA slate. So now we can see I've got all of my carbon number on this x-axis, and on the y-axis I've got homologous series. Yeah, so I've got alkanes, paraffins, and isomers, olefins, naphthalene, aromatics, etc. And also some impurity-based compounds, sulfur, nitrogen, vanadium compounds, which are associated with some carbon number component. So this is pretty neat because this all happens very seamlessly. In previous cases, we actually had to do quite a bit of manual manipulation. So that was my badly drawn hand sketch. This is what it looks like in your nice clean interface. So you'd essentially put in your boiling point curve, D1160. And as we know, whether you put in D1160 or D86, we need to translate everything into the normal boiling point. So in this case, we're using an Edmeister method to convert the D86 curve into like a TBP. So you put in your D86 curve, your D1160 curve, and then you would essentially define the parameters to allow the molecular decomposition to occur. Let me just zoom in with the magnifying glass. So let's take a look at some of this. So these are bulk properties, yeah. So this will be the bulk on that VGO and VR sample. 31 mass percent paraffins, isomers. So these are the bulk properties, yeah. These are the sulfur content, yeah. And then what happens is there's then a regression. So what happens is from the TBP curve, from D86, from D1160, you go to TBP. From the TBP curve, it feeds it into this molecular decomposition tool where you have all of these parameters. And then you use this regression. It's a regression decomposition tool. And what happens is it then generates, let me put this back to pointer because I need to, okay. I'm sorry, I'm going to turn this up. Okay, so after you've seen all that information go in, it then generates all these components. So from the TBP analysis and from PIONA, let me just go all the way up to the top. This is just an example of all the components that get generated. So as you can see, it's a lot more components than you would have if you were doing a typical TBP analysis. So you can see again here by carbon number and homologous family, C11 to C14 paraffins. You can actually set the resolution of this to see how fine you want to have these cuts. So now all these molecules have chemistry associated, and you can use them for your reaction sets. Yeah, aromatics. Yeah. Isoparaffins, naphthenes. So you have like a much richer composition. Yeah. So that's in a nutshell what this molecular decomposition tool does. So you can get from TBP analysis, from boiling point curve analysis, you can decouple all of those NBP components into these individual molecular definitions. So it's a bit. I find that sometimes when I'm talking about this, when I first saw it, I was really excited, and the other people who were really excited were my former colleagues who work a lot in this. But I think most other engineers said, "Oh yeah, isn't that how we did it before? Doesn't do the same thing." No, it's slightly different. It's a different way of sort of like defining your fluid. So now we have like a lot more detail on the individual components, on individual components which can be used for reactions. Yeah. So now that I've got all of these components, I can write my I can send them into a reactor model, and my reactor model can have all the kinetic relationships. Yeah. So I think if you go to, I think we've got some people here from academics. I know that I've still got some buddies in academics who are doing some research in refining, and I still see a lot of work done on this sort of molecular decomposition and lumped kinetic models. And at the end of the day, I think a lot of that research goes into these kinds of models over here. So I'm just going to switch over to the software, to the VMG, the symmetry software, and just show you what this looks like. Okay. So this is the tool. Their interface is it's a bit different from most of the tools that you've been seeing because it's based on Visio. So you need to actually acquire Visio and then use this as sort of that's essentially the GUI. So it's very similar to most of the flowsheet simulators that you're using. So these are the feed characterization drums that we have. So as you notice, I showed you like a range of all of the components. There's some smarts over here, so you can tell it if you're doing some work for refining or black oil. So there's also an upstream module for this, and you can put in your bulk experimental values here, overall density, and then later the routine will then generate the components to match this overall density. Yeah. So it kind of works, if you want to think about it, it kind of works similar to in theory to C7+. Yeah, so you put in C7+ component and then you specify some GORs or some dew points, saturation points, and then you tell roughly how many molecules you want to split up into, or there's some intelligence that splits it up into some N molecules, N plus components. It's a similar concept, but obviously things are more sophisticated here because you have things like PIONA, SARA definitions, and all the various PIONA definitions over here. They also have allow you to include some metals, and this is really important because ultimately these fluids are going to go into your reactors. So you want to have a handle on how these metals are propagating across your flow sheet. Yeah. That's all I'm going to say about this for the reactors. Again, I guess if you want to look at this in more detail, you can contact your friendly Schlumberger sales engineer, and I'm sure they can arrange for something more detailed to look at. So let's have a look at the reactor. So I'm not sure how many people here have done reactions. Again, maybe about 10, 15 years ago, when I was doing a lot of work in refining, we used black box models. But now, as you can see, these are fairly sophisticated models that we have here. Yeah, so this is for an FCC unit. You can have the riser in your details, or your riser characteristics. You can have your stripping section over here. You can essentially define the regen as well. So these are all characteristics. And again, I'm not going to go into this because this is worthy of like a training class on its own. If there's anyone from Pertamina or Schlumberger Jakarta, I think I ran this class sometime last year when we were free to travel all around the planet wherever we wanted to go. now we're doing a lot of these. That's why we have to use these teams now. But I think I was in Schlumberger sometime last year. So I think there are some ladies and gentlemen from Pertamina and ITB in that class. You can specify your CAT as well. So your zeolite type. You've got all the various options over here for that, yeah? And yield targets that you want to specify. So you'd run your reactor. I'm not going to run that right now because I run my company, so I have a management computer. I don't have like a nice Alienware or MSI machine, so I wouldn't be doing the software justice by running it off my my management machine. So this is okay for doing like a runs on my own. But I think if you want to have like a proper run, you probably need to use a proper engineering machine for this. So this is how the reactor works. If I take a look at, say, for example, the products over here, actually, let's go to some of the, say, gasoline, for example. So this is pretty neat. So again, I've got all my components, and you can see I've got a bucket load of components over here. Yeah, and they're kind of distributed. So in my feed, you notice that my components are more spread out. Over here, I've got more grouping, yeah, around this gasoline, around these middle distillate and aromatic sections over here. Yeah, if we can look at properties. So this is pretty neat as well. I can see the hydrocarbon properties, and these actually work. Yeah. So I can see essentially how my metals, if any, are distributed, how sulfur is distributed. Oops, there you go. I can see my vapor pressure, RVP, etc. Yeah, various components and PIONA details. I can take a look at some of my refinery properties. Some of the fuel properties, my RON, MON, cetane, methane number. Yeah, so there's a whole lot of exploring that you can do around here. So neat thing over here is because you've got all of these properties set up, you can do blending pretty nicely. So they work pretty well. Once you've got a good representation of these components. So you've got your reaction, your fractionation, and later when you're doing like your gasoline blending, you can. I think they've got some blending tools that they have in the tool palette over here. Yeah. So that's pretty much the reactor setup. Now, one thing about reactors, as you can see, I put a lot of detail. They've put in a lot of detail over here, and they've got, I don't know, maybe about anywhere in the order of magnitude about 100 reactions, 100 or so kinetic reactions, and you're solving that simultaneously. And then you've got flash calculations. So you've got all of these computations going on. So it's not, it takes time. If you wanted to use this tool for running quick case studies or for doing like maybe LP vector generation, sometimes using the rigorous engine, the rigorous calculation here might be too time consuming. So they've done something really neat. And I think at this point in time, they're probably the one of the few software environments that have done this. I mentioned back in the 90s, Hypertech had done this with HYSYS. So in the old version of HYSYS, there was like a neural net tool if you were using HYSYS in the late 90s. But now I haven't seen it. We called it neural nets. Nowadays, you refer to them as ROM, reduced order models. It got me really confused for a while because for me, ROM was rigorous online modeling. So in this case, we're calling it ROS, reduced order systems. So instead of having like the actual reactor model, what we can do in this case, with this reduced order model, so you can see over here in the in this particular module, I've got a reduced order model. You activate that checkbox, and you can actually run. What it does, it essentially replaces this rigorous model with something that looks like kind of a neural net. Now, apologies to the Schlumberger guys. I have no idea if this is what's going on under the hood. I spoke to James a couple of times, and I'm kind of guessing this is what's happening because there's only a few ways you can skin a neural net cat. So you would have various inputs that you can specify, you can train, kind of like using a case study tool. And then you have outputs. So one could be, for example, severity of operation. And then another one could be the RVP, yeah, of your product. So there's more cracking, more lighter ends, and then you have higher RVP for certain products. So this tool, once you've trained this this model, the training might take anywhere between tens of minutes or hours. But once you've gotten it trained, then it takes a matter of seconds to run. Yeah, and as far as I know, I think these guys are the only. I think Symmetry is the only tool to have this. I may be wrong, but I haven't seen it in any of the other tools that we've been using. Yeah. So, yeah. So that's a disclaimer. I'm guessing it looks like this. So, the Schlumberger team, you can ask James or Lante if this is true or if I just told a lie, but I think it looks like something like this. Okay, so that's all I have to say for this presentation. And again, just to reiterate what I was trying to convey, it was just sharing a new method of fluid characterization and reactor modeling. I called it ROM over here, ROS or ROM. I think it's a pretty neat way to look at fluid characterization, and I think this is the way to go. Because in the past, when I used to work in the refinery, something goes wrong with your naphtha reformer, then you call IFP and yell at them, and they'll send some French guy to fix it for you. These days, we probably want to be able to get a better handle on what's going on, because you've got a whole bunch of chemical engineers and process engineers in the field who are very capable of doing leveraging these tools. So. I think there's more. I think the future is going along these lines of these molecular decomposition or PIONA slate type models, yeah, because they're allowing us to model the reactors in better detail. So before I end, I just would like to have a disclaimer that we've not benchmarked or validated any results. If any one of you would like us to come in and try that, we'd be more than happy to benchmark. If you've got like some field data for that, so some of you guys in Pengerang, if you'd like us to have a look at maybe some of the revisit some of the models, the old not old but the HYSYS or refinery models, and you'd like to see how they function over here, we'd be happy to give you guys a hand. You can either talk to us or our friends over at Schlumberger for this. Okay, so that's all I have for now, and I'd like to thank you all for your patience. I'm going to hand this over to Zhihong. Zhihong will give a bit of an outro, and we'll have a question and answer session after this. Yeah. So thank you all very much for attending.
Thank you, Engineer Rafil Elyas, for an insightful and entertaining session. Thank you all for attending as well. The Q&A session will begin soon. We would like to take this opportunity to remind you that we have our next talk lined up. The topic is compressor analysis, surge protection. You can see it. Yeah. And the speaker, it will be Akila Jazuli, process engineer with close to 5 years engineering experience, will be taking place on Wednesday, 29th of July from 4 p.m. to 5 p.m. So that's 2 weeks from now. Special thanks once again to Schlumberger, who made this possible with Symmetry. For any inquiries, please contact Mr. Tung or Tung at the number and email address shown. We've also left this information in the chat box if you would like to copy and paste that. More information on their website, slb.com. For any inquiries about East 101 services, please contact myself, Zihong, or my colleague, Avinash, at the numbers and email addresses. Similarly, our contact information is in the chat box if you would like to copy that, or you can take a screenshot. Please visit our website. Please visit our website at east101.com to view the recording of this webinar once it is uploaded. Also, please follow us on LinkedIn to keep up to date with our activities. Just a quick reminder before we start the Q&A session. To keep things organized, please stay muted and type any questions you have in the chat box. That way we can go through them in order and there's no talking over each other. Thank you very much. And Rafil, please take it away. Oh.
Okay. Can everyone hear me?
Hang on, let me stop my control. I can't get that. Okay.
Okay.
Go ahead.
Discard. Hold on a second. Let me just turn this. Stop sharing. You can see my face now. We'll make sure I'm not picking my nose or anything. Can you run? Okay, so I'm looking at, are there some questions here? So we only got one person attempting to. There's a question from Dimas Ramadan Abdullah. Is this a kind of AI? Firstly, am I coming through? Okay. Zihong, Avinash, can you hear me?
Yes,
okay?
Yes.
Okay.
We can hear you.
So I'm just looking at the chat box over here. Let me just make it bigger so my old eyes can see. Dimas Ramadan Abdullah is asking if this kind of an AI. I wouldn't really call it an AI. I guess when I think of AI, I think of pretty much like an artificial intelligence or advisory kind of system. I always assume like AI is also, in addition to giving you some kind of like numerical predictions, it's also going to give you some heuristics. So I think this is more of like a neural net. And to me, I think a neural net is just, you can think of it as a neural net. It's kind of like I don't want to use this, I'm just going to use this analogy anyway. It's essentially some form of like a regressed model. A neural net is just a regressed model, but there's more interrelationships. So you can imagine it to be almost the modern version of your refinery LP. So when you train your neural net, it would be analogous to calculating the base and delta vectors for your LP. Yeah, except the neural net gives you, the LP just gives you linear relationships. Problem with linear relationships is after a while, things go non-linear. The neural nets actually allow you to have more curvature to your predictions. So I wouldn't consider it as a form of an AI. Yeah. So that's from Dimas.
Okay.
I see
let
another.
me read out the next question for the benefit of the other attendees. This question is from Christopher John, Mr. John. Some refinery products have distillation specs. How do you convert the PIONA data in the stream composition to distillation?
Oh, okay. So what happens over here, it's pretty interesting. Let me see if I can pull up that deck again. Hold on, let me get my slides. Oh, I think I need to share my screen. Share. Here. Okay. Okay, so here's actually something that you can do if you've got a simulator. If you've got a simulator on you. So what I've done is I've actually shown you the forward calculation. So from TBP curves, boiling point curves, I can actually do this decomposition. You can actually do this backwards as well. Here's an interesting, it's a computational property which are in all flow sheet simulators. Actually, getting from your molecules, if you have all these molecules, back calculating the TBP curve is quite easy, because all you're doing is you're essentially, if you can imagine, you're doing like some simulated distillation. So but you're doing it computationally. So you essentially have all of this material. Whoops, there's a pointer. Okay, all of these components over here. Imagine flashing this in HYSYS. So you can essentially simulate your TBP, D86 or D1160 analysis with this as your fluid, and you can regenerate these the TBP curves. Here's an experiment you can do if you have like any of these software tools. So if you've got like HYSYS Unisim around that family, you can actually punch in library components. C1, C2, C3, C4, C5, C6, C7, C8, C9, C10, C11. So input like some library components into a stream, give it some compositions, and then you can go into utility and say generate TBP curve. So that computation is essentially running like a simulated TBP distillation within the stream flash itself. So that's how they typically do it. And that's tech that they have even in like the more classic software tools. Yeah.
All right, thank you, Rafil. So far, I don't see any other questions. If anyone has any questions that they would like to ask regarding molecular PIONA-based feed characterization or anything related to refinery reactor modeling, please just type something up in the chat and we'll answer it to the best of our ability.
Okay, so Dimas is talking about, Dimas put some comment. I mean the reactor model input to output. The model you show is kind of like neural net. Yes, so it is like a neural net learning. But if you take a look at neural nets, I guess maybe I'm old-fashioned. I still call it statistical models. So for me, when I think of AI, I think of neural net being a subset of AI. So you'll have the neural net happening, but the AI might do things like triggering the learning or managing the learning and managing the output. So to me, that whole thing is AI. Yeah. So it is actually a neural net learning process. Yeah. Yeah. That is correct, Dimas. Okay. So we got 3 winners for East on 1 t-shirts. Make sure you pass us your email. So these 3 people, I don't know if they've actually used these cards, but that's actually what I learned my programming, my Fortran 77 on, and I did that before I went to university. I had a pre-university program in ITM. That's what now it's all UITM. So if there are any of people who are in ITM, Institute of Technology Mara, in the early to mid 80s, you would have probably been doing your chemical engineering programming using these guys. 76, there you go.
All right, we have a question from Farah S. Can you elaborate PIONA versus PONA without the I in perspective of reactor modeling?
Okay, that's a good question. Thank you, Farah. So I guess what we're looking at now is PIONA also takes into account isomers. PONA, I think the PONA analysis is only describing the paraffins, olefins, naphthalene, and aromatics. And if we take a look at some of the reactors, for example, the naphtha reformers, you're feeding in straight run naphtha, which is primarily straight chain paraffins. And you've got 3 reactors. And now this is, again, my organic chemistry is horrible. So whenever this happens, if there's any one of you from Petronas research, whenever I have a chemistry question, I always refer back to Dr. Shahida for any chemistry questions. So if you have any, if you want to know the actual reactions or going on in between, it should be the first person that you probably want to ask if you're in the Bangi campus. So we have the PIONA is, I guess, it's a superset of your PONA characterization. So we have all the functional groups or all the homologous groups covered, so that you could model your reformer, FCC, and all the other reactions. I shouldn't say we because it's not my software, but Schlumberger has this modeled. I hope that answers your question. It's, I guess, like a superset of all the functional groups.
I don't see a response from Farah yet, but thank you, Rafil, for that explanation.
Okay. Well, if there's no more questions, maybe we can call it an evening. Again, I'd like to thank all of you for logging in for this. I didn't realize we get that many people who would be interested in talking about fluid characterization. It's like I said, when this came out, I think there's probably maybe about 5 people I know that were excited about this, and I was very excited when I saw this this tool. So thank you a lot for coming in, and we hope to see you at the next talk. Akila Jazuli will be talking about compressor surge analysis. Yeah. So thank you all very much for logging in. Everyone take care.